Today I'm going to introduce our image processing project with the title Rice Counting. And our group member is Liew Kheng Yip, Chandy, and me, Jun Kiat. Now I will introduce our problem background. Assessing the physical characteristics of rice, such as grain, count, and size, is a fundamental process in the agriculture and food industry for determining yields, grading quality, and ensuring consumer standards. The traditional method of manual counting is inefficiency, highly susceptible to human error, and creates significant bottlenecks in quality control, making it impractical for large-scale, high-throughput analysis. Automated systems using image processing offer a modern solution, but they face key technical challenges. Not uniform background illumination can obscure grains, while touching and overlapping grains often lead to significant undercounting. And so our project, the objective is to develop an automated system in MATLAB to count rice grains from a digital image, to implement advanced image processing techniques to accurately segment touching grains and handle crumbs, to provide a fast, reliable, and repeatable method for rice quantification that overcomes the limitation of manual counting. And our methodology. First is image preparation. We will first load the rice image into the MATLAB. We will need to convert the image to grayscale to simplify the processing part. Next, we'll apply a morphological opening filter to correct for any uneven background, such as lightning, ensuring all grains are visible. And then we'll convert the corrected image into the binary, which is black and white format, and fill in any holes within the grains object and remove small noises, particles to clean up the binary image. Next, step 2 is watershed segmentation to split grain. We'll calculate the distance transform of binary image to find the center of each grain, and then we'll create markers of seeds for each grains by eroding the shapes. And then we'll apply the marker control watershed algorithm, which uses these seeds to build separations line between any touching or overlapping grains. Find the counting with count logic. We'll iterate through every object detected after segmentation, and then for each object detected, we'll check its area whether the area is within a normal size range for a single grain, so then we count the number as 1. But if the area is too large, I will estimate the number of grains inside the dividing counts area by averaging the grain area. And then we'll sum up the counts for all objects to get the final total. And it will loop every time until every item, every object is detected. And lastly, we display the results. It will show the original image, and then we'll draw color boundary around the detected objects. Green for individual counted grains and red for estimated clumps. And then we'll display the final completed grains count on the image tile.
Hello, I'm Tanji from S132. Today I'm going to talk about the counting rice code for the image processing. This is a standard clear off, first off, clear command. For this testing, we will use rice-free image, which is this one. This is just error handling. If the image is not found, it will just output the thing. For the rice, we can either use default, which is 0, so that the program will estimate the single rice area for us, or we can set the pixel ourselves, 200 to 300 something. For this part, if the object is larger than the estimated rice times the max object area factor, it will be counted by division. For this, it will display the original image, which is this one. After that, it will have 3 more figures. 1, 2, 3. This is just checking if the image is RGB. If not, it will just use back the grayscale. If it is, it will change to the grayscale. For the figure 2, you can show as here. This is after the background is corrected. The disk size equals to 30. After that, the image will change to a binary image. After that, the image will change to binary image. If any hole is big, it will get filled, such as this one. This hole will get filled, it will become like this, and then clean up afterwards. So here, we'll change to a binary image, fill the holes, and remove the smaller noises. After that, the next step is to estimate the rice grain, which is to check the manual rice. This is to see if we have manually set the rice. If not, they will just count the rice and then measure their area average. Next, the system will estimate the single rice radius and then erode away smaller rice grains. If there's a speck of rice, it will just be removed. This is to ensure the minimum erosion radius. This is to define the minimum area for final objects based on estimate. This is the formula. And then after that, this will be printed out. The next one is to check the max single object area. Means if I want to set the maximum area for a single rise, I can just change this and then times the max object area. The next step for the figure 3, we are using the watershed segmentation steps. This is the figure. For this part, we compute the Euclidean distance transform, which is this. Then we generate the markers by erosion. Here, the figure, it shows that the marker eroded based on this. So that convert the markers to the label image, which is like this. And the final step is to clean up and count with max area logic. So this variable will be initialized. Boundary for the plot, boundary colors, text labels. This is for displaying the rise in the current area, which looks something like this, with a 9 at the side. As you can see, you can count the rise like this: 1, 2, 3, 4. This is accurate. 1, 2, 3, 4. This is accurate. 1, 2, 3, accurate. 1, 2, 3, 4, 5, 6, 7, 8, 9, accurate. But some of the rise with a larger boundary will be discounted as 4, but that is very low chances. This is to check for the bigger cloud, just like the line, something like this. And it will ensure if the area is above the minimum final object area, the number of estimated cloud will become 1. So it means here we have 1, 2, 3, 4, 5, 6 cloud. If not, the total final count estimated in cloud. For the boundary color, it's just for setting the oversized clumps, which is red. This also assign green color for the single grains which are not stick or clumped together. It is just displaying the final count. The last step is to display the final result for the figure 4 as we seen before, which is this figure 4. We have the final result, this object counted as subplot. This is for plotting the boundary, setting color and the line width.
Hello Goggle, my name is Liew Kheng Yip and I will now be presenting our output. For our figure 1.1, this shows the original image used for the counting rise project, and for figure 2 it focuses more on the cleaning and isolation of the rise gain using the method shown in methodology. For a good figure, this part focuses on separating the overlapping rise string. Without this part, the overlapping rise strings will be counted as only one rise string. For figure 1.4, it shows the total amount of rise string in the picture, which is 55 rise string. The green outline of the rise string represents non-overlapping as shown in the diagram here, and the red outline represents overlapping rise string, which shows the number of the rise string in a clump. Based on the result, it is clear that the experiment was quite successful in determining the number of rise strings in the pictures, which is 55. So, in conclusion, this study has shown the experimentation of counting rise strings using MATLAB image processing tools. There are a few techniques used to improve counting, which helps to get close to the correct amount of rise strings within an image, like separating the rise strings. For example, counting the area of a rise string clump to be divided with the area of a rise string could approximate the number of rise strings within a clump. The result shows pretty decent improvement with better counting results such as 55 rise strings for the first image and 192 rise strings for the second picture. So this is our reference here. We use this for link to find the images here. Thank you.